Okay, so thank you very much for coming. So the topic we will discuss today, so as you know, we will be covering two topics, bi-level programming and three-stage programming. This week we will do the bi-level. So what I will do is that I will give an introduction, I will give the definition, the mathematical definition for the bi-level programming. I'll give some history, some of the well-known applications for bi-level, and some examples to just to connect the dots between the mathematical definition and the numbers. So bi-level programming problems are a type of hierarchical optimization where an objective function is to be minimized over the graph of the solution set mapping of a second parametric optimization problem. So we have two optimization problems. One of them is called the lower level, the other is called the higher level, and the solution of the lower level is used to find a solution for the higher level. The set of all variables is partitioned between vectors x and y. Before we get into the mathematical definition, so I will just show some of the applications, well-known applications for bi-level programming, and there are few. There are not so many applications because it's very difficult to solve these type of problems. So one of the applications is the toll setting problem. The high level here is the government. The government tries to set the toll in order to maximize their revenue. And the people here are the lower level. And what they try to do is that they decide their utilization of the highways based on the prices or based on the setting of the tolls. If the toll is high, the utilization will be low. If the toll is low, the utilization will be high. And we try to find a balance that cover the interests of both parties. The second application is power system vulnerability analysis. So in the upper level, we determine a set of simultaneous outages in the transmission network. So it's like an attack on the infrastructure where the attacker is trying to affect the transmission system within some constraints like budget or resources, while the defender reacts to this outage and try to minimize the losses as much as possible. In cybersecurity, the hackers try to access private. So,
hello, Sushil?
Yeah.
Can you put the camera, your phone to the middle of the projector? I cannot. Yeah.
It's fine?
Perfect.
Okay. Okay. And okay, so we stopped here. Cybersecurity. So the hacker decides which private servers to access, how many of them, based on some restrictions in the resources. The defender decides the security budget, that's needed, and the level of security that has to be there to minimize the attacks, again within some constraints. Okay, so this is the mathematical definition. Please feel free if you have any questions to ask. It's more like a lecture than a presentation. So given y, the vector x is to be chosen as an optimal solution where x equal to x of y of an optimization problem parameterized in y. So xy belongs to C of y, and C of y is the collection of the solutions that are feasible to the lower level problem and the upper level problem as well. So you put all your constraints, you see what feasible region you will get. Those are the solutions that are feasible for both. And it's equal to the minimization of f, x, and y subject to some constraints g of x and y. F is a real number, and we will have p number of constraints g. This problem is called the lower level problem. And as I was just saying, the point to set mapping C takes the x values into pairs of x and y's with the power set 2 to the power Rn. And that's the solution set mapping of the lower level problem. The solution x of y is called the rational reaction of the follower on the leader's choice. This is how they call it.
Is this the whole definition of bi-level?
No, this is half of the definition.
This is lower level.
This is the lower level. When we go to the higher level, we have a minimization of f of x of y subject to g of y less than or equal to 0. And notice here that we have only y because x is fixed from the previous level. And x has to belong to that.
So
C.
x is now parameter for this.
X is like a parameter, yes. More or less.
What do you mean by more or less?
Because when you try to solve it, it is a variable. Once you solve it as a linear, once you solve the lower level problem, it becomes a parameter. So it depends on which stage you are at. F is a real number, and we will have Q number of constraints, G.
So your y can be both binary or integer,
Whatever.
Okay.
This problem is it's called the leader's problem or the upper level problem, and there is an assumption that is necessary in bi-level programming. I don't know why, but this is what I found. F capital, G capital, F small, G small has all have to be sufficiently smooth. By sufficiently smooth, we mean that
Continuous
it can be continuous functions, but this is half of the answer. It has to be differentiable, and we have to get at least the gradient and the Hessian. That's why we have sufficiently, because smooth is like infinitely differentiable. Sufficiently has to be gradient, and the Hessian have to have the gradient and the Hessian. Some history. First time
So that means they are convex functions, right?
Not necessarily.
Not necessarily.
That's what makes it difficult to solve. It's not convex usually, most probably, even if in its simplest forms. So I will show some examples that are very simple, yet they are not convex. So the first to use the term bi-level was Candler and Norton. The first formulation appeared in 1973 by Bracken and McGill, and the bi-level problems started to get attention in the early 80s. It has been the topic of a large number of papers, but real-life implementations are very scarce due to the very small number of algorithms available to solve. Okay, so I will give you two simple examples, just to show you how it is easy to solve it numerically when it is small. But even when we can solve it numerically, using an algorithm will be difficult because it won't be a complex problem. So suppose we have in the lower level C of y, which is again the feasible region. It's equal to minimization of minus xy subject to x between 0 and 1. And let's have an upper level model where we minimize x squared plus y squared. And x is m deeps in C, and y is between 0 and 1. So what we do is that we evaluate first the lower level, then the upper level. What we do is that we determine the intervals, we determine for each value of y, what's the optimal x for that problem, and we keep all those pairs and use them later when we solve the upper level problem. So,
Isn't it like they are giving more emphasis on the lower level than upper level? Isn't something like that?
Yeah. So what I understood from my readings is that lower level problem determines the optimal solutions, optimal x's for all the y's. Okay, so it's like the best of the best.
More clearer when you will see some real application. Let's wait to see some real application, then things will be more clear.
Okay, so suppose that y. So we here can have three different situations. if y is less than 0, that term minus xy will be minus x multiplied by a negative, so it will become a positive. In order to make this as few as possible, we set x as 0. Is that clear? When y is more than 0, in our case, let's assume that it is between 0 and 1, minus xy will be equal to minus x. In order to make this as negative as possible, we set x as big as possible. X cannot be more than or equal to 1, so this is the optimal solution. If y is equal to 0, it doesn't matter what value for x we choose. Any value between 0 and 1 will be the optimal for that lower problem. So now for each y, we know what the value of its x will be. What we will do is that we will take each pair of y and x, plug it into this minimization problem, and see which one gives us the minimum. So doing that, when y is less than 0, we plug it here. It will be a positive term, regardless of what's the sign of y. Plus x squared is equal to 0, so 0 plus y squared is equal to y squared. If y is more than 0, it will be, if y is more than 0, x is equal to 1, so it will be 1 squared plus y squared, or 1 plus y squared. If y is equal to 0, any value for x will suffice. And you can see clearly here that the optimal solution is 0 and 0. This is the optimal solution that we get based on the pairs of optimal solutions of the lower problem. Another example that is a little bit more complicated. So the lower level is the minimization of minus x, subject to these three constraints. The upper level is the minimization of 3x plus y, subject to y between 1 and 6. Again, what we do exactly like we did before. We evaluate the lower level, then the upper level. And we can clearly see something here. Actually, it's not very clear unless you draw it. It will be much more clearer. Out of those three constraints, one of them is always tight when y is between 1 and 3. And by, I hope you know what tight is, right? When a constraint is tight. So a constraint is called tight when the summation of the left-hand side is equal to the summation of the right-hand side, and that choice for x and y is also satisfactory for the other two constraints that are there. So when we see that when y is between 1 and 3, the constraint 2x plus y less than or equal to 13 is the one that we need to satisfy, because once we satisfy this to tightness, the other two constraints are automatically satisfied. So when y is between 1 and 3, the solution that we get is that for x is 13 minus y divided by 2, so it's 6.5 minus 0.5y. This is the optimal solution for x, for any y between 1 and 3. When y is between 3 and 6, we see that this is the most crucial constraint to satisfy. Once we satisfy that, the others are satisfied. So the value of x is equal to 8 minus y. Any value of y, we plug it there, we find the optimal x. So now we found each pair of y and x from the lower level problem. We plug each pair into the upper level problem and see which one gives us the minimum value. So this is the value of x, 6.5 minus 0.5y. We plug it here instead of x. So 3 multiplied by 6.5 minus 3 multiplied by 0.5y plus y. This is equal to 19.5 minus 0.5y. Whatever y we have between 1 and 3, this is the x. This is the value, the optimization value that we will get for that pair. If y is between 3 and 6, x will be between 8, will be equal to 8 minus y, and this is the objective function, the optimal solution that we will get. And if you try all the combinations, the optimal point will be equal to 2, x equal to 2 and y equal to 6 with the objective function equal to 12. So it sounds easy, but the case is not. So this is the graph of the constraints. This region M is the feasible region for the when you consider the constraints by themselves. This is the feasible region. The C region is actually these two lines. And what these two lines are, they are the values, they are the pairs of values of y and x that we found from the lower level problem. When we plug them, they give us this piecewise linear function. So if we concentrate on this piecewise linear function, we will find that it is non-convex, it's non-differentiable. So if we have an algorithm to solve, we cannot be sure if the solution that we get is a global optimum or local minimum or a saddle point. Okay, so this is the third example. This just shows a formulation that I found in one of the papers. No numbers here. So can
you explain the previous slide one more time?
Okay, so when you draw all the constraints, the feasible region that you will get is the feasible region M. Before solving anything, before solving the lower problem or the upper problem, this is the feasible region that you will get. Once you
feasible for lower level problem.
Feasible region, if you consider all the constraints isolatedly, all of them.
Lower level, upper level.
Or together, all together. When you solve the lower level problem and you find the pairs of y and x, you plug them. When you plug them, you will end up with this piecewise linear.
Okay.
So this first part is a representation of this, and this second part is a representation of this.
Yes.
Non-convex, non-differentiable. Even in its simplest form, linears, it's difficult to solve with an algorithm. So this is an example for a total optimization I found in one of the papers. So they found that in this bi-level model, the leader's objective, which is this objective, is non-continuous, not continuous, and not convex. And they had to do some transformations that I didn't get the time to understand exactly what they are, but they do some transformations in order to make it convex and continuous, and transform it into a mixed integer programming equivalent model that can be solved with any computer software. That's all I have for you today. Any questions?
One of the major point that, as I talked to you before, the underlying concept about what we have shown in the first few slides are really important. But to imagine that what's really going on, we need to kind of solve some real life problems and see how that somehow gives a better understanding. So this might be something that if you can address in the next week.
Sure.
Okay. So providing some.
So you mean the week after next week?
So next week, I think next week you can do it, right? Next Thursday.
Okay. Yeah, because I remember we said first that it will be every 2 weeks. Lecture every 2 weeks.
I'm fine. I
Okay.
mean, if you think we need 2 weeks,
Okay.
well, essentially what we need. Hello.
Zeus, do you have any question?
And does it? Are you hearing us? This isn't.
This number.
Dishnu, do you hear us? Do you hear what we are saying?
Is there?
Are you hearing us?
Hello.
Yeah.
Hi. I couldn't hear anything, so can you please send me the video?
Oh, okay.
I sent you an email. If you could send me the video and slides, because the audio was so, I couldn't hear anything. Like in the beginning I heard for a minute and then it was so breaking up.
Okay.
So how about Sushil, you send the video, okay?
Okay.
To Jishnu.
You have video, okay?
Yeah.
Send it to me, then I will send to you.
So that's fine. You don't have to record anytime.
Okay, I'll send you the video, okay?
Okay. Thank you. Is there another one? Is there another presentation now?
Not today.
Not today. So Vishnu, the next presentation will be next Thursday. I mean, not,
Next Thursday?
not this Thursday. The following Thursday. Following Thursday,
Okay.
right? 1 week. So again, Sushil will send you another email about